Welcome everybody to CS Kaksha, and today we'll be basically solving a problem called LRU Cache. So this problem is very widely, asked upon during interviews. So let's just dive right into it, and we will be solving it in C++. So the first thing what we would be doing is that we would be just going through the question, and after that we will be trying to understand the concept in the whiteboard over here, and then once the concept is understood, we will code it in LeetCode, and then we'll try to once it's done, once it's accepted, we'll also try to look into the edge cases and try to make the existing code a little better. So let's just get right into it. So what does this question is asking? So it's basically asking us to design a data structure that follows the constraints of least recently used LRU cache. Okay, so what happens over here is that we've got to implement these particular classes LRU cache. We have to implement the get function, and we've got to implement the put function. Alright, so get function is pretty much that you return the value of the key if the key exists, otherwise return -1. And input, what we've got to do is update the value of the key if the key exists, otherwise add the key value back to the cache. And now this is where the concept of LRU comes into the picture. So which is, if the number of keys exceeds the capacity from this operation, evict the least recently used key. So this is where the entire game is about. So if suppose, it's very simple here in get. So what basically get does is that it gives you a function where you've got to give a parameter called key, and within the data structure that we are designing over here, if that key exists, we have to simply return that value, right? So that's pretty much what get's asking us to do. And put over here is pretty much saying that if the key is existing, you update it with the recently provided value over here, which is also given in the parameter. And if it is not, you have to just add it, right? So if this line was not existing, if this line was not in the picture, it would have simply been a normal LRU, a normal map, hash map, or in C++ unordered map, right? It would have just been that. But since this comes into the picture, which is if the number of key exceeds the capacity from this operation, evict the least recently used key. So this is where we've got to design a data structure, whereas we are somehow keeping a record of which is the least recently used element, and when the capacity exceeds the capacity which is mentioned over here, once the number of input exceeds the capacity which is given, we've got to evict or delete the least recently used here, right? So to evict the least recently used key, we should be having a record of which needs to be deleted, right? So this is what the question is asking over here. So let's try to visualize this over here. So over here, let's say that we've got some get over here, get, right? So let's say get 2, and let's say put 2 comma 2. So over here, this particular thing is the key, as mentioned over here. This is over here in this function, int key, get is int key, and put is key and value, right? So over here, when this comes into the picture, let's say this is the data structure that we are designing. We will detailedly discuss regarding what this is. But over here, let's come over here. So right now there is nothing which is there over here which we are going to design. So it returns -1. So this case is given over here, that if the key value does not exist, we have to return -1. So yeah, so this is empty over here, and put 2 comma 2, right? So now what we'll do is we would be basically putting the key 2 with value 2 here. So now once again, when we get 2, we can basically ping this over here, this can pinged over here, and over here this can result in 2. Let's say we say instead of 2 comma 2, I don't want it to be confusing, so let's say it's 2 comma 8. So this is the value here, this is the value here, and this is the key here, right? So 2 comma 8 is put, so 8 is coming. So now the constraint in this particular question of LRU is the lookup should be in O of 1 time complexity, right? It needs to be in O of 1 complexity. So everything that we've discussed over here and previously as well, it simply points to an unordered map, or basically a map, right? Since we do not need to basically store the sequence in a way, so instead of map, it's unordered map, right? Now the second thing that comes into the picture is which is the least recently used map, right? Which is the least recently used element. So for that, what we would be doing is basically, if it's least recently used element, right, what I would be doing is, okay, if this is the map over here, let's say if this is the element over here, right, so I can say the element which is over here, the leftmost element, let's say that this is the least recently used element over here. We can just say that this is the least recently used element, and we can say this is the most recently used element over here. So we can just basically sort or sequence the data structure in such a way that we can basically have one end as the least recently used element and the one end as the most recently used element. So what we can do over here is so what comes into the picture is, suppose if there is an element in between, and suppose if we are basically looking this up, suppose we are looking this up, right? So what needs to be done is, once we've basically checked this element, this needs to come on the most recently used element part. So this needs to be basically deleted from here, it needs to be deleted from here, and then it needs to be added over here, and it needs to be added in the head. Right. So this part also needs to be done in O of 1 complexity. So this part also needs to be done in O of 1 complexity, and it needs to be done in constant time. So over here, if this was a vector, what needed to be done is, if we are removing an element in the middle, we had to basically move all the elements in the left hand side to one step towards the right, and then it would basically ask us to traverse. Suppose if this is the holes, let's say this is m elements and this is n elements over here, we had to basically move all these elements one by one towards the right. So we cannot choose a vector or simply a list. We need to choose an element where we are able to somehow traverse both towards the left and towards the right. So for this situation where we've got to basically have bidirectional movement, and we have full freedom to move anywhere and connect anywhere, and to be dynamic also, we are basically using doubly linked list for that. And since we want O of 1 lookup, we are using map. So the dynamic data structure over here, it says, right, design a data structure that follows the constraints. So this particular data structure is basically an unordered map. Basically it's an unordered map right here, which is basically which is having a key and a node pointer, and all these kind of, basically this unordered map is connected to each other. So these node pointers are connected to each other via a doubly linked list. So this is what the data structure is. So this is what we are going to do. So we are going to have an unordered map, and which can basically have the key as the key, and node, basically a node. Now what this node is, this node is basically will be having the key, the value, and it will have the connection towards the previous node, and the next node as well. So this will become our doubly linked list. So this is the data structure that we would be basically using. Okay, so now as I mentioned over here, right, so all we've got to do is, whenever get comes into the picture, let's just discuss about the get function here. So suppose if I am calling a particular element, let's say this is the particular element over here, let's say this is x. So I will be deleting x from this particular position, and then I will be adding x in this towards the rightmost side. This is what I'll be doing, and yeah, and if this was put, again I will be just updating the value of that element, and then again I'll be deleting that element from that position and adding it over towards the right hand side. So the moment we're adding or stacking up more elements towards the right hand side, which we have discussed it to be the most recently used, so, or obviously the previously one which will be at the left hand side will be the least recently used naturally. So if we are making sure that whatever we are using, we are stacking it towards the right hand side, eventually what will end up in the left hand side, the leftmost side, will be the least recently used, right? So over here, let's to facilitate this, we will have two dummy basically in the doubly linked list we'll just have a two nodes, which is head and tail, and this element over here can be the LRU, and this element over here can be the MRU, the most recently used MRU. The reason we are maintaining two dummy nodes head and tail is for that we can easily have a lookup. So the tail next would be immediately giving us the LRU, and then head previous will immediately give us the MRU. So you will see in the code that it's very, the key concept here is to make sure that we have the tail and the head as a dummy node. Okay, so let's just directly go towards the code over here. So as I discussed here, we will be basically first having a node. Let's say it is a structure. So structure node, and over here we would be having the key and the value, and we will be also storing, since it's a doubly linked list, we will be also storing the reference of the next and the previous nodes. And let's just have a constructor over here which we can assign so that this particular node key value pair is basically populated. So this value is equal to value. Yeah, so pretty much this is it. This is our node structure, and this is the dynamic data structure which they wanted us to basically design. So unordered map int comma node pointer. So this is the data structure that's needed. The node pointer over here, since it has connections to the previous and next, automatically becomes the doubly linked list that we were wanting. Unordered map is over here, which will be giving us the O1 lookup to this node pointer, and node pointer will be giving us access to the previous and the next elements. So let's just say this as um. Okay, so now let's just design the dummy pointers. So node pointer head is equal to, let's just assign this dynamically, -1 comma -1 over here. And yeah, so -1 over here is basically the key value. The reason we have kept this as -1 is so that by mistake there is no key collision where there is a similar key with a particular element, right? So -1, we are making sure that it will not be the case. All the key will be positive. Hence, we will not make sure that it just head overwrite with some actual node. So that's the reason it's been kept as -1. Okay. Similarly, we've got to do it for the tail as well. So new node -1 comma -1. So over here we have assigned the head and the tail. So in this LRU cache, let's just connect these head and tail. So head next, let's say this is as the tail, and tail previous is the head. Now you can say that in LRU cache we are also being received with the capacity. So let's just have a global capacity over here. So let's say this is the capacity, and yeah, this dot capacity is, yeah, so this capacity is equal to the capacity. Instead of using this, what we can also do is, like, we can follow a certain pattern as well. We can have the private variable starting with underscore, and so underscore capacity is equal to capacity. The reason we need to use this is that the variable name is same, so that the compiler understands the scope correctly and it's able to distinguish between the scope of the variables. So we've got this as the capacity over here, and I think, let's see, pretty much this seems to be good. Okay, so now in the get function, the first thing, let's say, let's just say if that particular map has that key or not. So if we say um.find key is equal to um.end, what does this mean? So if suppose this map has this key or not. So if it's equal to um.end, that means the map does not have the key. So in this case we can simply return -1. Okay, you don't have the key. Suppose if we have the key, so line number 25 crosses it, and if it goes to line number 26, so we can just store that node pointer. Let's say this is the get node, which is equal to key. So this is how we are accessing the node pointer from the key, and we are storing it in the get node. So now what needs to be done is, so once we've received the get node, we've got to delete it from the actual position and then add it back. So let's, for now, what I'll just say is, I'll say delete node get node, and then add it back, add it in the head, add node, and that's it. So this particular function, what it will do is we will define it. So this function deletes that node at any position which it was, and this particular add node, what it does is it adds it towards the rightmost side. That is basically if this is the head, so head previous will be the most used element, most recently used element. So add it towards the rightmost side, that is over here, that is previous of head. So I think, yeah, and return ultimately get node value, because we've got to also give the value of that particular key, right? So the reason we've got to do these things is because we have to maintain the LRU sequence, and otherwise just a simple map lookup should have given the root the answer for this particular function. So now let's define this delete node and add node. So okay, so what this delete node does is, it takes in a node pointer. Let's name this as del node. And okay, so what it does is, okay, so I'll explain it over here. So for example, so suppose this is the tail, this is the head, this is the del node over here, and this is the previous node of del node, and this is the next node of del node. So if I simply connect these two things over here and then pretty much remove it, right? If suppose right now they have the connection over here, right now if I do not invoke this delete function, we have this connection over here. So if I break this connection over here and if I add this connection over here, so this particular node will automatically become isolated. So this particular node will automatically get isolated if I just rearrange the connection. So that is what we are going to do. So I'm going to name the functions variable so that it's very straightforward. So let's just say, what is the next of del node? It is del next, as simple as that. And what is the previous of del node? It is del node's previous, as simple as that. So now let's basically break the previous connection and add it. So it's simple. All we have to do is if del node dot if next del node, let's just say that is next del node previous is equal to preview of del node over here, prev del node, and prev del node's next is basically next del node. So what this does is it basically rearranges the connection. It basically, instead of this connection it makes this, instead of this it makes this. That's it. So this particular variable is become isolated, and I can reuse this particular connection and bring it towards the head add node. So over here let's just say void add node here, which will be getting the node pointer add node. So what we will do here is basically we will just add it over here. Similar thing. So basically this was the MRU, so we'll just name this particular node as temp, and then what we will be doing is head node as this, the node which we are going to add. So we'll just say head previous is this, then and the element which we are going to add, and add node next is equal to head. So it's just the play of connections over here. So the current MRU, let's just say this is the node pointer, and we'll just name it as temp, for example. So temp is equal to head previous. So this is the current MRU which we are going to replace, and then we can just say you are no longer the head previous. Head previous is now the add node, and add nodes next is basically head, and add node previous is equal to temp, which was previously the MRU, and temp's next is equal to add node. That's it. So over here these two functions takes care of all the connections over here, and now the only thing that is missing is adding it in the adding it in the map. So over here let's just say once we've done this, once we've deleted this, we can just say dot erase, since we've deleted it, the key and we can say the del nodes key is basically the key. We can just delete it from the map, and once it's added, we can just add also that particular key and just say this and map it to the add node. So this is how the map also is getting taken care of. So we can make sure we can basically get the of one lookup in the get function. Now comes the put function. So in put function, first thing let's check is whether it's present or not. So if um.find key is equal to um.end, that means it's not present in the unordered map, then we've got to add it, right? Then we've got to add it, but we can only add it if suppose the if there is capacity for it, if there is space for that, right? So if the capacity is greater than greater than or equal to um.size, so then we've got to evict, and we've got to evict basically, right? We've got to basically delete the least recently used element, because if suppose there are only size of 3 here, right, and there is only 1, 2, 3 over here, when 1 being the LRU, the least recently used, and 3 being the MRU, the most recently used, and if I want to add 4 over here, I've got to delete this thing over here, 1, 2, 3, and basically add 4 here. So this ultimately becomes 2, 3, 4. So when this thing happens, what I'll be doing is I'll delete that particular LRU node over here. So I have to basically call the delete node function. So let's say, okay, so node pointer LRU node. So this is the LRU node. So LRU node is basically the tail next node. So that is the reason I hope you are able to understand why we are maintaining 2 dummy nodes, tail and head, to basically get a lookup of the adjacent elements in a very fast, an O of 1. So this is the LRU node. So all we've got to do is delete node of LRU node. And since it's no longer required anywhere, we can also erase. Okay, so that is already happening over here, and basically removing it from the map. So delete node basically takes care of removing it from the map. And since we no longer require that node, we can also delete that address also directly from the address register as well. So once we've done this, so we have space. So we can simply say add node of that particular node that we wanted to create. So the new node which will be having the key and value, because add node only basically contains only accepts node as the parameter. So that's the reason we are having add node, new node, we are basically key and value which we provided. So this is the particular function for if suppose there is no value here. Suppose if the variable already exists and you have to just update it. So at that point, let's get the put node over here directly. So put node, we can directly get it from the map using the key over here. So right now we have the put node, and what we'll do is we'll delete that node, because since it's been called again, it's been used again, so we're going to delete it from that place and add it here, add node here, add node, put node over here. But before adding it, we've got to update the put node's value with the one which is being provided. That's the whole reason of update, and then add it over here back in put node, and add and delete function will take care of basically erasing and adding it in the map, unordered map again. Yeah, so I think pretty much that's it. See, so it was very simple. So over here we were very easily able to make sure that the value, if it is existing in the map, updating that value, and if suppose that value is not there, and if the capacity is more than that, we can delete the LRU, or if suppose if we've got capacity, we can directly just add it over here, right? Okay, let's see the moment of truth. I hope we get some errors. We'll try to debug it live. Okay, so we've got some error over here which says um.erase use of undeclared identifier. Okay, the reason we've got this is because I have basically declared this function outside the class, which should not have been the case. Since unordered map is only defined inside the class, so yeah, that is the reason. Now let's run it. So I've put it back inside the class now, and key is what they're not able to understand. Key. Okay, so over here, see, we are basically passing the add node, right? I cannot simply directly call upon key. I have to access it via the add node. So now basically add key. Now that error should have been gone. and capacity, right? So over here, the capacity over here has the scope only within the uh, constructor over here. So that we can make it global, that's the reason we had initialized it in the whole place, and it starts with an underscore over here. So that's the reason it needs to have underscore over here. Alright, let's see. Okay, there is runtime error. Member access is misaligned. Okay, that means there is some null exception. So over here, the reason this happens is, for example, if there is null exception, there is nothing in the address over there. Address does not exist, but we still try to access that address. So that's the time null exception comes into the picture. So let's see why this happens. A small mistake. So over here, it should be head previous, which is equal to tail, and this should be basically tails next, because tail is on the left hand side and head is on the right hand side, right? We've kept it like that. So since we've had this logic like that, that is the reason we've kept it. And over here we can just say this as equal to. If capacity is reaching the size, we can evict it directly, and it's accepted. Let's try to run it. Yes, I think we are good. Okay, let's try to make this a little more sharper, the code. So over here you can see that we are basically in get function, we are deleting the node and adding the node. So over here we can see that it basically removes it from the map and adds it back again. So it basically, the removing and addition should not have been done, right? Because if we don't do anything, it's still the same. So what we'll do is, we'll basically make sure that the map part is basically handled directly from the code and not from these functions, helper functions. So over here the get function becomes a more sharper code over here. And once we are trying to delete this LRU node, because this is where we're actually deleting it and just not rearranging, we can just erase it from the map over here. So LRU node key. So we've made these changes. Let's try to run this. It's the wrong answer. Okay, and then when we are adding it over here, we need to also add it over here. Okay, because the key and the new node pointer that we have just created. So let's just say that this is the addition node, add node equal to new node key comma value over here, and let's just say that we can say that this is the add node here. Yeah, else we're adding it over here, so it's already there. So yeah, pretty much I think this should do it. Okay, it's because of this extra bracket. Okay, let's just say this is as underscore here. When we run it, we are getting the answer. So I'll share this code in the description. There are many more improvements that can be done and make this code a little more sharper. I want you to do that and basically add that in the comments. I will be also adding the improvements that can be done in this code in the comments. So the code, you can find it in the description, and the ways that we can make this code a little more sharper can be found in the comments. So please do consider subscribing. It really does motivates me to make more videos, and I am planning to make more such videos in the future entirely for free. So yeah, thank you so much. Thank you.